Don't just pick some random problem either. No? Crickets, huh? Crickets.
I'm going to be honest.
Yeah, I'm gonna be honest too. Like,
No? Y'all haven't looked at it?
I
Okay.
didn't do it yet.
Okay.
I did one though, I guess, I thought it was part of the homework problem, but it wasn't. But I did end up doing 11. And it was similar to question 10, but it gave you I guess a constraint with the material available.
Yeah. You want
Try
to?
to do that, I couldn't get it.
Okay. You want to go through that one? Sounds fair to me. All right. Number 11. We have, if you have 1,200 square centimeters of material to make a box with a square base and an open top, find the largest possible volume of the box. That's all they give you. Okay? So you have to get some drawing going on here. You have a box, three-dimensional box. So when you try and draw something like a box in 3 dimensions, start with the front of it, and then just take the corner back, take that corner the same distance, and then just come down and across. I don't know if that makes sense how I did that, but you'll see that. Take that front and then just draw lines back. Make sure these lines are parallel. All right, so you've got this box in 3-dimensional space, but it tells you that it has a square base. Square base. So that means that if I were to imagine the inside, the bottom of this, right, that bottom piece there is a square. Then, and it has an open top, which means that this box doesn't, I could reach my hand into the box, yes? Which means if I drew it, it would look like that, wouldn't it? Something like that. Put my hand in there. All right. I have 1,200 square centimeters of material to make this box. I need to make it in a way that I get the largest volume possible. What are the dimensions of the box, right? Or no, just find the largest volume, which I'm going to have to come up with the dimensions. So we have two things that we're always trying to do with these. Find our objective equation, and then at some point we're going to have a constraint, aren't we? So what is the objective equation here? What is it, the thing that we are trying to find the maximum or minimum of?
volume.
Volume. We want the maximum, right? We want the maximum volume, which means I need a formula for the volume of this box.
X cubed.
X, so X, you're going to say X is this side from here to here? And I can say that from here to here is also X, right? But I cannot say that this is X because they said it's a square base, but it didn't say that it had to be as high as it was wide.
Could it be?
It could turn out that way, but I can't say that yet. Okay? So how about we call this height from here to here? Why don't we call that H? Okay, that's fine. Call it H.
I don't understand why we couldn't assume that was X.
Because it doesn't say it was. It says it has a square base.
Mm-hmm.
If you assume that the height is X, then it's a cube, right?
Yeah, I mean, it doesn't say it's a cube.
It doesn't say it's a cube. So it could be a cube. It might turn out that H is X, and that's the way you'll get the most volume. But it could also turn out that it's not.
Okay.
So imagine you could have a box like this. Maybe it's 2 by 2 by whatever this is, right?
Mm-hmm.
Or you can make it really, really wide. I'm going to run out of room here. Something like that, right? These two boxes have square bases, different heights, different volumes. So which one has the most? What dimensions? But I can only use this much material.
What if we already know that having a cube would give you the most volume? Can we not assume that?
What's that?
Having a cube will give you the most volume?
Yes, it will give you the most volume to have a cube.
We can't assume that.
but it also depends on how much material you have and how much box you're making. See, this box doesn't have a top, right? Which is going to mean that the material can be used, it doesn't have to be used for this top piece. So maybe it's not going to be a cube. Let's see where it leads us. So would you agree right now that the volume of this is x times x, x squared times h, right? I would like to figure out if I can find this in terms of one variable. Right now it's in terms of two, right? So I have to use some sort of constraint. And the constraint is the physical limitation on the amount of material I have. So like if this was like the cardboard, if I'm making this out of cardboard, or if I'm making it out of aluminum or some sort of metal, that's how much surface area I'm allowed to have, right? So this is my constraint. My constraint is that the area must be 1,200. Now when I say area, what I mean is all the sides together. So can you give me some idea of what the area, the surface area of this box is?
X squared.
X squared, so that's the bottom, right?
Right.
X squared, the bottom times the bottom, that's x squared plus,
4xh.
so this side right here is x wide and h tall, and then I have another xh, then the back side another xh, then this side over here, right, like right in there, that's another xh. So I have four of those, 4xh, so I'm adding that. That must be 1,200. So do you see how this formula would change if the box had a top? If the box had a top, it would be what?
5xh. Or 2x.
2x squared, right? 2x squared. So I'd have one on the bottom, one on the top. Go with me? All right, that's my constraint. Now what?
Solve for h and plug in.
Solve that one for h and replace this h with whatever I get over there. I think that sounds good. So I'm going to solve that for h. When I solve it for h, I move the x squared over. And I divide through by 4x. So when I divide 1,200 minus x squared by 4x, I can split that into two fractions, can't I? And 1,200 over 4x would be 300 over x. And then minus x squared over 4x, what? X over 4? I'm going to write it this way, 1/4 x. Is that the same as x over 4? Okay. With me? Take that h now and replace this with that. So the volume will be x squared times the entire quantity, 300 over x minus 1/4 x. And distribute that x squared through now. The volume is now a function of x, isn't it? I only have one variable in here now. It is 300x minus 1/4 x cubed. That is my objective equation, but now as a function of x. That's what I want to find the maximum of, right? Do I have, well, I kind of almost gave it away there. What do I do next?
We have to figure out if it's closed or open.
That's right. Is it closed or open interval?
It's closed.
Closed.
Okay, if it's closed, you have to be able to tell me the smallest x can be and the biggest x can be.
Well, it can't be any smaller than 0.
It can't be any smaller. Can it be 0?
No. Can't have negative or 0 distance.
Yeah.
Yeah, think back to your picture, right? X was this base, right? If that's 0, this side's 0, you're not going to have any area, are you? You'll have no surface area. you're supposed to have 1,200 square centimeters. So x can't be 0, right? It could be a little bit bigger than 0, though. So I'm thinking this is going to be on 0, and then is there a biggest x can be?
We have to figure that out.
Yeah.
Well, what would it be? Infinity? So there's no biggest? What do y'all think?
There'd have to be biggest than
Yeah, because eventually it'll overflow.
because you only have 1,200 centimeters squared of material. So
Okay.
the next section is you have more.
So if I made this thing like super, here's my box, right, like this, and I make my height infinitesimally small like this, can I still get 1,200 square centimeters? If I make it short enough, right, the bigger I make x, the shorter h would have to be, wouldn't it? But I can't cap x off anywhere. I can't say, you know, it's got to be this. If I make x 1,000,000 centimeters, I could find an h small enough to still stay at 1,200. Does that make sense? So you don't have a restriction on x. So it's an open interval. So that changes the way I'm going to attack the problem. I'm going to have to do it by investigating the derivative and look for where the function goes up and then down, right? So let's take a derivative. The derivative's nice. That's your derivative, right? And to find the critical numbers, we set that equal to 0. So 300 minus 3/4 x squared equals 0. And go ahead and solve that. Solve that yourself and plug in test points and see what you get. Would you mind, Emilio, turn on the projector for me? Thank you. I always want to say Emilio. I don't know why I say Emilio. Ramiro, right? Plus or minus 20?
Yeah.
But you throw one of those out, right? Because x can't be negative. So x is 20. Now, do you have any places where the derivative is undefined?
No.
No, because the derivative is a nice polynomial. So we don't have to consider that, but I will at least show that I did think about it. Is it undefined anywhere? No, don't worry. So is this it? X is 20, I'm done? You have to test it, all right? You have to show that x is 20 is a maximum. So the only way to test it and be sure is a number line and 2 test points. And those 2 test points will get plugged into the derivative. So if you plug 10 in, what happens to the derivative here? 100, 3/4. It's going to be positive, right? 300 minus some number smaller than 300. So it's going to be positive, so it means our function is increasing. Plug in a number that's really big, you know, whatever you want. You'll see this is negative. And now you can conclude that x gives you a maximum, right? Questions? We're not done. We want the volume, right? So we have a maximum at x is 20. We have a max volume at x is equal to 20. But I had an equation for h. H was equal to 1200 minus x squared over 4x, right? And if I plug in 20 there, h would be 1200 minus 400, which is 800, over 80, which is 10. 10? So now I actually know the dimensions of the box, don't I? The volume of the box was x squared h, which would be 20 times 20 times 10, which would be 4,000,
Yeah,
right? 4,000 cubic centimeters, because it's a volume. So if I'm going to build a box with 1,200 square centimeters of material, and it's going to have a square base, then this is the way I'd build it. I would build it so that this was 20 centimeters, this was 20 centimeters, and this was 10 centimeters. If I do it that way, I'm going to use all 1,200 square centimeters of material. I'm going to get a volume of 4,000 cubic centimeters, and there's no other way to build that box using that much material and get a box with greater volume than that. That's the absolute best way and most efficient way to do it. Make sense? Okay. So back to our instinct was that if you make it a cube, it's going to work. But because the box didn't have a top, that changed things. What I'm going to do up here is I just want to graph. I want to graph the volume function. What was the volume function? The one that we were going to find the maximum of?
The original function?
V of x.
V of x is 300x,
300x minus
x cubed over 4.
x cubed over 4. And we were on the interval, let me see, 0 to infinity. So I'm going to go 0 to 50. I'm going to have to change my view a little bit here. Left, 50, down, up. Our maximum volume was what? 4,000, so I'm going to have to, let's look at 4,500 high. Ah! I think that's good enough. So this is the graph of the volume function. It's a cubic polynomial. If I zoom out even more, well, I only drew it from, let me not restrict it. There's the cubic function, okay? But we're only looking at a certain part of it. We're only looking right in here, right? The right side. At some point, the volume became negative. It's kind of weird, right? Somewhere around here. 30. That's kind of odd. But where did the maximum occur? Right there. At x was, what, 20? Which is somewhere in here. All right, I hope that that makes sense. We found the highest point on that graph right there. Now, was it the highest point on the entire graph? It was a local max, but in the interval that we were looking, it was the maximum. So we were only looking from 0 to the right. So it is the maximum over there. Okay. Any others? I like that box problem. That problem, if no one would have asked me about that problem, that would have been a completely fair, legitimate problem to put on the test. So just to give you an idea, like that right there, work through that. It's good you asked, but all of these problems are, the first, what did I give you up to? Like, I don't know how far I went, but any of the ones I told you to do would be fair game. Let's do one more, all right? And then we're going to just put this behind us. And then if you have additional questions, maybe next class you'll have more questions on it. I want to look at number 23. And I want to look at 23 because this is a classic problem. And the wording of it is something that people, maybe for the first time, it's like you've never heard something like this. It says a right circular cylinder is inscribed into a sphere of radius r. Find the largest possible volume of such a cylinder. Now let me give you a little bit of background as to like the origin of problems like this. These problems come into play if you're trying to optimize packing. You're trying to pack things onto a truck. You have to pay for that freight to get it across the country. You want to be careful how you pack things, right? It's like when you're packing moving or something. You don't just throw everything in the van. You pack things up nice and neat so that you can get the most stuff in the smallest amount of space. So let's imagine that we have a sphere, okay, with the fixed radius of r. All right, so let's start with the sphere, three-dimensional. So how do we draw a sphere how do we draw a three-dimensional sphere on a flat sheet of paper? Well, we draw a circle and then we just do something like this. There's your center point. Okay, that's our best rendition of a sphere on a flat piece of paper. And then we have a right circular cylinder. Now, what's a right circular cylinder? It's a beer can, right? And what I want to do is I want to put this beer can into the sphere. And I want to know the largest volume possible for such a can. But it must be inscribed. So what do we mean by inscribed? Well, what we mean is that you see this top edge of the cylinder right here, this top ring? That top ring is going to hit the sphere. So if I put this in here, it will hit somewhere up in here. And then it will hit down here. Like that. Do y'all see it? Now, will this cylinder touch the North Pole? No, because if I give the cylinder width, then it has to come down a little bit, doesn't it? But the more narrow I get, the higher up it's going to go into the sphere, won't it? So that's one way I could do it, right? Now, just on the side here, I'm going to draw a couple of other ways I could do it. I could do something like this, where it hits just barely up there, barely down there, right? So I have a very narrow cylinder inside of the sphere. That's going to have a certain volume, won't it? Yeah? Or I could go, and I could make a very wide sphere, but the wider it gets, what? Shorter it gets, yes? So I could have a cylinder that is in here like this, like that. Make sense? So the way I drew it, it would almost appear that the wider it is, the more volume I would get, right? The wider it is. Well, what happens if the radius of your cylinder becomes the radius of your sphere? You have no volume because the height would have to be 0. Understand? So somewhere in between here and maybe somewhere between there and some like infinitesimally thin little thing like that, somewhere in between there, there's the optimum solution. It's the cylinder with the largest volume possible. Yes? Let's find it. Okay, so start where we always start. Everyone understands geometrically what we have, though, right? Start with what we always start with, which is objective. What's the objective function here? Volume of a cylinder, right? Not the sphere, cylinder. So the objective equation is going to come from the fact that we want the maximum volume for the cylinder. All right, so what is the volume of a cylinder? Pi r squared h. That formula relies on two variables, r and h, right? Let's use, hold on. In this problem, do you know how I said that the sphere had a radius of r? That's fixed, right? I don't want us to confuse it with this radius, because this is the radius of the cylinder. Two different things, right? And in the book, they don't tell you that. So we need to either change the r that's fixed to something other letter, or we need to change this to a different letter. What do y'all want to do? The r that's fixed, what do you want to make it?
Big R.
Capital R?
Yeah.
Capital R? Okay. So let's, just for note, capital R is the radius of the sphere. And it is fixed, right? That is a fixed sphere. It's not moving. Hopefully it's not. So I have an equation. It has the volume, which is what I'm trying to maximize, right? I'm trying to maximize that volume. And it relies on two different variables. So I need to get it down to one. So I need a constraint, don't I? What's my constraint?
The maximum radius.
The volume of the sphere?
The volume of, well,
The radius of the sphere.
the radius of the sphere is fixed, right? So that is constraining me in some sense. But it has to help me eliminate one of those variables. The volume of the cylinder, that's what we're trying to figure out what's the highest, or where it's the highest. So it's not our constraint, it's what we're trying to figure. Something else, somewhere else, is going to allow me to eliminate h or r from this equation.
Volume of the sphere.
The volume of the sphere. Do you know what the volume of the sphere is?
4/3 pi r cubed.
4/3 pi r cubed, yes. But does that have h in it? See, to eliminate r or h, I need to come up with the relationship between r and h, don't I? So yes, even though I do agree that we do know the volume of the sphere, it does not require us to know h, which is the volume, which is the height of the cylinder. Not to mention that the volume of the sphere has nothing to do with the radius of this one either. This radius is different than that radius. So it's not quite.
Can you say that h couldn't be any bigger than 2r, or too big r?
So you're coming up with some restrictions on h, right? Like h, that height is restricted. The width of this, we know that little r here is restricted, right? The radius of that cylinder inside can't be smaller than 0 and can't be bigger than capital R, right? So this one, the reason why this is a classic problem is because it's not obvious what the constraint is. So what we're going to do is I want you to go back to that picture that I drew and take a look at this. Imagine coming through right now with some sort of cutting device, and I want you to just cut this sphere right down the center, okay? With the sound effect, yes, thank you. Thank you. All right, so you cut it right down the center, right? And then you peel it open, and you throw one half away, and you're looking at the cross-section. What does that cross-section look like? It's a rectangle inside of a square, isn't it? So there's, a rectangle inside of a circle. So there's the sphere, right? And inside of it is a rectangle. And this is where you can kind of see that inscribed part that you can tell it would not quite make it to the top, right? The center is somewhere in here. Got it? All right, let's take a look at some things we know. The distance from here to here is what?
R.
Which one? Little r. Remember, all we're trying to do is find the relationship between little r and little h, right? Any relationship we can find. What else do I know on this picture? The height, which is from here all the way to here, right?
Which is H.
Which is h. So I'm going to put that out here just so we... That is h. I agree. What else do we know?
Would NH equal to 2D or 4R?
Yeah, we know big R.
We know big R. Wait, well, hold on. H is what?
4R because, wait,
Okay.
wouldn't be,
No?
because it's missing the other space.
Yeah, it just depends. Like if I draw this shorter, it's going to be wider, and right? We know big R. Where's big R on this picture?
From the midpoint all the way to the end of the circle.
From the midpoint to any point on the sphere, right?
Right.
Any point? Any point. How about that one? Right? Capital R? Fixed number? Do you see what I'm creating here?
Yeah.
All right, I have a right triangle, and I actually know this side from here to here is what? Half of h. Right? It's half of h. This is half of h. Do I have a relationship now between little h and little r? Yes, but it's in terms of capital R, but that's okay, because capital R in this problem is going to be a fixed number. That may as well be 100. It doesn't matter, it's fixed. So let's write down the relationship. I know by the Pythagorean theorem, sorry, that r squared plus 1/2 h squared is capital R squared, isn't it? This is standard protocol for problems like this. Inscribed objects and other things, to cut them in half and then look at the geometry of that and try and come up with a relationship. Okay. I'm going to put this. I'm going to square this, because that's where people make mistakes also. Square the 1/2. Make sure it turns into a 1/4. Now, what do you want to solve for? H? Look over there at your objective equation. Oh, look, this one has r squared in it, doesn't it? Isn't this one easy to solve for, r squared? If I just move this over, don't I have it r squared? So could I solve it for h? Yes, I could, but if I did that, it's going to require square root at some point, isn't it? I'm going to avoid that completely by solving this for r squared. Little r squared. Okay, so this is my constraint, right? This is my constraint. I didn't put it here. Constraint is here, And now I come back to my volume formula. The volume will be pi r, which little r squared, which is actually big R squared minus 1/4 h squared, but then times what? H. Now, is this volume now a function of a single variable? Yes, because capital R is a constant, right? It's fixed.
So is that V of X now?
We're going to say V of H.
V of H.
V of H. Everyone with me? All right, so V of H is pi capital R squared H minus pi over 4 H cubed. See if I did that right. I distributed a pi through each of these, and I distributed an H through to each of these. Everyone agree? That's my objective function. So now I need to see if there's a restriction on H. Is there? Go back to your picture. What's the smallest H could be?
0.
0, right? What's the biggest H could be? You don't want to bust out of the sphere, right?
Yeah.
So go back to your picture. Hold on. Go to that cross-section picture.
Yeah, but yeah, it can never be big R.
So the smallest H could be would be nothing, right? And the biggest it could be would be, it would be R one direction, R the other direction, 2R? So let's see. Go ahead, Weber.
Wouldn't you never touch the edge of the sphere?
If H, okay,
With the corners.
yes, if I let H be 0, right, then this would go, and it would just be a disk, wouldn't it? With no height to it, which would have no volume.
Right.
I would never do that, but would you agree 0 is going to be like the lowest I'd ever go? It would be stupid for me to even try it, but yes. And then the other thing is to let H be 2R, which would mean that you would have to touch the top and the bottom, which means your cylinder would be a straight line, and it would have no radius to it, right? Which would be the other extreme, which would be ridiculous, but I think we can safely search just in here, can't we?
So how come it's closed intervals? How is the bracket versus the?
Because you can't blow through the circle.
Are you saying why is it not open? Or why can't I keep going?
Well, like, how come you
I'm
can't
off
be
my
0
camera.
or 2R?
Why can't you?
Couldn't you theoretically never be 0 or 2R?
Theoretically, you would have no volume.
Right.
Yes. So it's like me saying, hey, go put a cylinder in this sphere, and you choose a cylinder with 0 height. And I'm just like, you're fired. You know what I'm saying? But it does give you some restriction as to how far you can go. And then capital 2R is the other way. You know, you're going to put a line from top to bottom. It's theoretically, though, look, in this function, can H be 0? Look at the function right here. Forget the problem of the cylinder and the sphere. Can H be 0 here? Yes. Can H be 2R? Yes. So there's no problem algebraically with me letting it be 0 and 2R. But what it allows me to do calculus-wise is do the closed interval method, which means that I just need to find a critical number, whatever it is, plug in that into the function, and plug in the endpoints. I already know what's going to happen at the endpoints, though. I should get 0 volume. So let's take the derivative. So derivative, be very careful here. The only variable in the problem is h, right? So pi capital R squared is a constant times h. Derivative of h is 1. So this is just pi capital R squared minus, again, this is all constant. So 3 pi over 4 h squared. I need to set that equal to 0. Solve it for h. I'm going to move the negative stuff to the right and make it positive. I think I went off my camera here. Divide both sides by pi. Multiply both sides by the reciprocal of 3/4, which is 4/3. Capital R squared equals h squared. And then take the square root on both sides.
So this is just choose a number for R. You just help it out.
Say again?
Would you choose a number? For
No,
R?
I wouldn't. I'll show you how I'm going to do it. That's the critical number, right? Right there. So now, what I'm going to do is I'm going to plug in, because it's a closed interval, I'm going to do v of 0, v of root 4/3 capital R, and v of 2 capital R. Yes? That's the two endpoints plugged into the original function, the critical number plugged into the original function, because I'm using closed interval method. I already know what's going to happen here and here. So whatever this answer is going to be where we have a maximum. Right? So let's plug in. Any questions on how I got this?
Well, how come the capital R isn't within the root? So it is 4/3 capital R squared.
I took the root of R squared though. So it's like I did the root on both of them separately, and then this one was just the R. Yeah, we have to be real careful. This R is not underneath there. It's separated. All right, now the volume function I erased, but it was v of h was pi r squared h, right, minus pi over 4 h cubed. Are y'all impressed that I remembered that? No? You're not? What I actually did to do that is I took the antiderivative of this, because I knew this was a derivative. I took the antiderivative of this in my head, which is what we're going to talk about today or next class, which is how you go from here back to here. Right? I went from here to here, and I just mentally went back to this. It's not like voodoo magic. It's just, you'll see. Okay, now let's plug in 0. What happens when we plug in 0? That's easy, right? Plug in 0 for h, 0. All right, let's plug in, should we plug in 2r? Let's just see what happens. V of 2r. Replacing h with 2r, pi, capital R squared times 2 times capital R minus pi over 4 times 2r cubed, right? And when I cube 2r, I get 8r cubed. 8r cubed. Over here, what do I get? 2 pi r cubed. But when you reduce this fraction, 8 over 4 is 2. You get 2 pi r cubed. So 2 pi r cubed minus 2 pi r cubed is 0 again. So I get no volume here, which, again, we kind of knew would happen. But this one is going to be where I get a maximum. So I've got to plug that in. So V of square root of 4/3 r is pi times r, capital R squared times h. H is root 4/3 times capital R minus pi over 4 times root 4/3 r cubed. Whatever that is. I'm going to clean it up, but you understand what I'm doing? Just plugging it in? Because I think it says here, find the largest volume. So whatever this answer is the largest volume. It'll be in terms of capital R, though, right? I'm not going to get like an answer like 5 or something. It's going to be, capital R is going to be in there. So this will turn into, let me clean it up. I have r cubed, right? I have r cubed here. And this root thing I'm putting in front of the pi. So we've got root 4/3 pi times r cubed. Over here, I have minus pi over 4. When I cube the r, I get r cubed. Now, what happens when I cube this? It's it times itself times itself times itself, right? So what happens when you do it twice? Root 4/3, root 4/3, root 4/3. These two just become 4/3, right? So I have 4/3 times root 4/3. Yeah, I can simplify the 4. I think I will in a minute. Y'all okay with this? This 4 and this 4 cancel. I get pi over 3 there. So root 4/3 pi times r cubed minus pi over 3 root 4/3 r cubed. Anybody see any common factors there?
Root 4/3.
Root 4/3
And r cubed.
and r cubed and pi all come out, right?
So pi r cubed.
I'm going to do root 4/3 pi r cubed comes out. What's still in there? 1 minus 1/3, right? What's 1 minus 1/3? 2/3. That's 2/3. I'm going to put it in front. 2/3 times root 4/3 times r cubed. Forgot my pi. Yes, I did. I'll put it right here. Pi r cubed. Almost there. I'm ready to clean that root up now. Do the square root of top and bottom separately. So what's square root of 4 on top? 2, and then times the 2 on the other one. 4 over 3 root 3, right? Pi r cubed. Remember rationalizing denominators? I can multiply the top and bottom here by what? Root 3. Root 3. I don't have to do this, but, right? I don't have to. I'm wondering what the back of the book will have. 23, 4.5. They have 4 pi r cubed over 3 root 3. So they have this. So they didn't rationalize. All right, so that problem is, I probably wouldn't give you something like that on the test where it was like capital R. You know, maybe if I said like the radius was 5 or something so that you could actually get a nice number to work with. But I wanted to show you that because it's a classic problem where you take it and you cut it in half and look at the cross section. Some other ones that I've seen that I remember as a Cal 1 student sitting there going, what the hell's going on here? It was very confusing. My professor was somewhat confusing though. Where you get something like this. You have, how about a sphere again? I'm not going to do this problem just to think about it. But instead of a right cylinder, put a right circular cone. Okay? So how would that change things? Well, you'd still go through a setup, you'd still cut it in half, but now when you cut it in half, your picture is going to look like this. You know the height of your cone is this, right? You know the radius of your cone, little r, is this. And you know the center is right here, right? So you have to come up with a relationship now. Anyone see we can do?
Pythagorean again, right?
Pythagorean? So where?
Yeah, from the height, that's the triangle, so down the middle.
Like this? From here to here?
Go to left or right.
And then, what, like this?
Yeah.
Then here to here? Something like that you could do? This is capital R. This is little r. Is that half of h?
Yes.
Yes? You're sure of that?
Well,
Is it? Is it? See, that's different. Do we have the same symmetry that we had with the cylinder? I think everyone with the cylinder agreed that the top and the bottom were equally up and down, right? But can you say that that's what this is?
well, I mean, we'd have to know if that was an equilateral triangle, right?
Is it, though?
You can get the
Right.
triangle now.
Yeah, but I mean, we'd have to know that it was, to say that it was 1/2 h.
Yeah, you would have to know that, but it's not. So you can't say that that's half of h.
Yeah.
So what would it be?
Well, you could use the Pythagorean theorem to find out what that length is.
How?
I mean, we'd have to know what the variables were, but we could find out.
R squared.
The square root of r squared minus r, big R squared minus r squared
Yes,
would give you that.
I agree, but you need a relationship between r and h. You need an equation that relates r and h together here. You want to work with the entire half instead? That for sure is h, right?
Would it be,
Yeah.
would it be h is equal to like big R
Do y'all want to try that for bonus?
plus?
Yeah.
For a quiz?
For a bonus.
Oh, for bonus.
Yeah.
Yeah.
You want to try it for bonus?
Yeah.
I'll give that as a bonus problem.
Can you write that down here?
So you are taking a sphere radius capital R. You're inscribing a right circular cone into the sphere. Find the maximum volume of such a cone. So it's everything that the last problem was except a cone instead of a right circular cylinder. But I'm warning you that this is not half of h right here. And but there is a relationship, okay? And maybe it's not this. Maybe you need to just take a step back. I'd say that for sure is not, that for sure is true, right? That's true. The center to this corner is capital R. And so is that. That's also capital R. Right?
So, trying to find the height of the other column?
You're trying to find an equation that connects little r and capital H together so that you can go eliminate it in the volume formula for the... I'm going to let you play with it. That's why it's bonus. All right.
Can we work together? Like classmates?
As long as you're working together, yeah. I prefer you don't go to the tutoring lab and say, hey, I got this bonus problem. Can you show me how to do it? I mean, that's kind of not the point, but... Yeah, you can work together. But not right now. We're going to move on. All right. So, Newton's method is the next section. And I don't like to put these problems on the test, only because Newton's method. Because they're really computational, and I don't like computational problems, all right? But I want you to see Newton's method, because I talked to you about it before. There was even a problem, I think, last class where we waved our hands and said we could do it with Newton's method. I want you to see how Newton's method works. And I was thinking about this on my way into work today. I was like, how in-depth do I want to go? Because it's a formula. I could just give you the formula, or I could actually derive the formula. I haven't derived the formula in several years, so I thought it would be fun to derive it. All right? So let's see if we can figure it out. All right, so here's the idea. Newton's method. This is, yeah, 4.6. This is kind of one of the more primitive ways that computers solve equations. So imagine that I have an equation. And let's just take something simple. X squared equals 2. We all know that the solution to that is what? plus or minus root 2. But what's root 2? 1 point, why? Because your calculator told you, right? Okay, now how is your calculator getting 1.414, right? How is that, where is that coming from? So what we'll do is this. We take an equation, and first thing, we move everything to one side. X squared minus 2 equals 0, right? And then we look at the left side of this as a function of x, right? There's a function of x. And forget the equals 0. If I asked you to come in here and just graph, all right, everybody, we're in college algebra. Let's graph x squared minus 2, everyone. Then you would draw your x and y axes. You would say, well, that's a parabola, right? It's been moved down 2. And you come in here and go 1, 2, and you know that point exists. It's obvious because if you plug in 0, you get negative 2. And then you'd say, oh yeah, it has x-intercepts, right? And where are the x-intercepts? Well, you would have to set that equal to 0, which is equivalent to doing that, right? Which is equivalent to the original equation. So going back again, what we're doing is we're starting with an equation, saying how do we find the solutions? We move everything to one side, we call that a function, and then what we say is we just want to know the x-intercepts of this function, right? If I know the x-intercepts, finding the x-intercepts, right, of f is equivalent to I don't think I have enough room. Is equivalent to solving x squared equals 2. Do you all see that? Finding the x-intercepts of this function is equivalent to solving this equation. All right, so here's my graph. I know it does something like this. Goes through like that, right? Okay. Now, how does Newton's method work? I just want you to see the setup, at least, the beginning of this. We are interested in the x-intercepts of a function. So what I'm going to do now is I'm going to blow that picture up. Here's 1. Here's 2. Now we know, because we know, it's 1.414, something like that, right? That's where it comes through. Here's the way Newton's method works. Newton's method, what you do is you start with what we call an initial guess as to what you think the answer is. So when you're looking at this, you guess 2. Is 2 squared equal to 2? No, right? But it's your initial guess. So if I were to come over here and I would say, hey, is it 2? You would say no, right? But I want you to go up on the function to 2 and see that point right there, right? How high is that point? Where is it? If we plug in 2, where is it? On this function? It would be at 2, wouldn't it? Okay. Now, look at what happens. If I look at the slope of if I look at the tangent line at that point. Okay, here's the tangent line. Look at where that tangent line hits the x-axis. Is that closer to the true x-intercept? Yes? All right. But it's not, right? It doesn't look like it is. So this right here, this first point, x, I'm going to call x sub 1 was my first guess, right? My second guess is this point, which I'll call x sub 2. Now watch what happens. If I plug that into the function, I'm going to get a value up here, right? Now take the slope of that tangent line, or take that tangent line and bring that one down. And what's happening? Aren't you getting closer to this answer? That's the idea of Newton's method, is that as you go, the derivative starts to point you